Welcome back, everybody, to the last part of the AMP1 chapters and narrated PowerPoints. We are in chapter 15, autonomic nervous system, and through the first part of the lecture slides in chapter 15, we have seen this concept of dual innervation. We also have seen a large number of gross anatomical details, parts of the sympathetic and parasympathetic division. When it comes to the target organs, we have two pictures here. One is the heart, the other is the stomach, and we are going to follow the actions of the parasympathetic and sympathetic division of our nervous system on these two organs. When you look at those images from the first part, you see that there are a large number of organs in the body that have dual innervation. A little bit we'll come back to that later on when we talk about the detailed physiological effect on the entire body of the parasympathetic and the sympathetic nerve impulses. Please note the color scheme here. I know that the first part of the chapter, your book publisher uses blue for sympathetic and red for parasympathetic. Later on this switches. So when we get into the molecular effects and components and participants, your textbook changes color code. So you'll see that blue in this part will be representing parasympathetic, and red in general will be representing sympathetic division. So what is the advantage of having dual innervation? The advantage is that we can slow down the activity of a particular organ, so we can decrease the heart rate by one set of nerve impulses, and we can increase the heart rate by sending more of the other type of nerve impulses to this organ. The hypothalamus is a big decision maker in this respect. And so whatever our hypothalamus decides, this is what happens to these organs. So here is a little bit of a conundrum. How is it possible that nerve impulse, that flow of sodium and potassium ions coming down to the end of the axons through the parasympathetic and sympathetic division can cause such a different end result? The nerve impulses are identical in their nature. They are flow of sodium and potassium ions. So obviously what is happening here at the end of those nerves make a big difference. And here is something that we have looked at a little bit in chapter 12. Looking at different neurotransmitters. You had a table in chapter 12 of your textbook naming and showing the structure of different neurotransmitters. Even in that chapter I mentioned and we looked at inhibitory neurotransmitters. So that's the first inkling that neurotransmitters released from the parasympathetic axons and the sympathetic axons are most likely to be different, and they are responsible for either the slowing down action on the heart or the speeding up action on the heart from the sympathetic division. So let's take a look at these neurotransmitters. We have a little bit of terminology. Good thing that we will see a very familiar player, the adrenergic neurons releasing acetylcholine. So here is the red color coding for a sympathetic postganglionic neuron, and look at the label. NE means norepinephrine, and here is a cholinergic set of neurons releasing acetylcholine. So indeed, the target organs see two different chemicals when they are stimulated by nerve impulse from the sympathetic division. They are seeing the release of norepinephrine. When the target organ, the same target organ, is stimulated by the parasympathetic division, blue here, those target organs and their cells see acetylcholine in their environment, and those cells are basically reacting to these two different chemicals. So it kind of makes sense that when it comes to acetylcholine release, all parasympathetic postganglionic neurons are cholinergic, releasing acetylcholine. What happens in the ganglia, all preganglionic neurons, no matter what it's connected to them here, are releasing acetylcholine. So here's the situation for our parasympathetic division. Whatever is the target organ, acetylcholine is released as soon as a nerve impulse gets to the axon end bulbs, whether it's the heart or the stomach. So those cells of the heart and cells of the stomach must detect this neurotransmitter. We have seen several examples of ligand-gated channels. Remember the acetylcholine-gated sodium channel in chapter 10 on the surface of muscle cells. So those type of receptors can pass on excitatory or inhibitory reaction in the cell. Nicotinic receptors always cause excitation. You would guess that this was opening of the sodium channels. Activation of the muscarinic receptors can cause either excitation or inhibition depending on the cell. So inside the cell, there is a set of reactions that may be different in different organs. The way this shakes out for the heart and the stomach is that in both cases, acetylcholine is released from the cholinergic neuron. The cells of the heart detect acetylcholine through muscarinic receptors. It's the same for the stomach. However, the activity of the heart decreases when it is receiving acetylcholine detected by muscarinic receptors. The stomach does the polar opposite. Stomach activity increases when acetylcholine is released from parasympathetic axons. So we see a very different reaction. Heart activity decreases when parasympathetic nerve impulses are sent there, and you see the steps here. On the other hand, some other organs, activity is increased when parasympathetic nerve impulses are released to them. At the end, we will see a combined effect on many organs of the effects of parasympathetic and sympathetic nerve impulses. This will all make really magnificent sense for maintaining homeostasis. And then we have the release of norepinephrine from the adrenergic neurons. So this red neuron is adrenergic because it releases norepinephrine. The old name of norepinephrine is adrenaline. This is where the adrenergic name comes from. So adrenergic neurons release norepinephrine. This also excites or inhibits the organs depending on receptors. Now for norepinephrine, we will see a number of different type of receptors on the target cells. So here's our starter situation. Yet again, no matter which organ it is, sympathetic nerve endings will be releasing norepinephrine when a nerve impulse is coming through here, whether it's a heart or a stomach. And here are the receptors. So some organs have alpha 1 and beta 1 type of receptors. These are just different names for proteins that are ligand-gated, either ligand-gated channels or proteins that can transmit information to the inside the cell. So alpha and beta 1 receptors create excitation in that target organ. If the target organ has alpha 2 and beta 2 receptors, that target organ will be inhibited by norepinephrine. How is this happening for the heart and for the stomach? Norepinephrine is released. The cardiac muscle cells and some other cells in the heart have beta 1 and alpha 1 receptors. The stomach has beta 2 and alpha 2 receptors. So the effect of those alpha 1 and beta 1 and alpha 2 and beta 2 receptors is that the heart responds by excitation, heart rate increases. The stomach responds the opposite way, stomach activity will decrease. And when we say stomach activity in the digestive system, we'll go greater detail. Production of digestive enzymes decrease here, stomach motility, the mixing, the churning of the stomach decreases. So overall stomach activities, digestive activities decrease. So and once you have this all laid out in molecular terms, now I hope it makes perfect sense that when the hypothalamus decides to send parasympathetic nerve impulses through all the circuits, the craniosacral, motor nerves, heart rate will decrease, stomach activity will increase. When the hypothalamus, in its great wisdom, decides to send an overwhelming sympathetic nerve impulses through the thoracolumbar circuits, right? These nerve impulses have different bundles of spinal nerves carrying it. Norepinephrine will be released at the target organs, and the effect will be different depending on whether the target organ has alpha 1 beta 1 or alpha 2 beta 2 receptors. Who in their right mind could possibly decide which organ gets which set of receptors? So during embryonic development, the group of cells that decide that, hey, we want to be heart cells, they will start a genetic program that will make alpha 1 and beta 1 receptor proteins inside those cells. During embryonic development, the cells that want to be stomach, and they say, yes, they do say, hey, we want to be a stomach. So they start a different genetic program, and those cells will have now alpha 2 and beta 2 receptors made, and the mature organs will retain these receptors. The effect of parasympathetic and sympathetic division is decisive on the action of life-maintaining organs. We have seen the heart, and you may say the stomach is not really a life-maintaining organ. Well, we do need the digestive system to bring water, vitamins, electrolytes, energy carriers to our body. So we actually do want that digestive system function perfectly. When something can, from the outside, change the activity of those receptors, we can call them agonists. And agonists speed up the activity of that neurotransmitter. Antagonists are chemicals that will inhibit the effect of those neurotransmitters. So there are a large number of examples. For example, let's take a look at an agonist. And later on, we'll come back to it. One effect of our parasympathetic division is to narrow the pupil diameter. When you go to an eye exam and the optometrist want to check out your retina, sometimes eye drops are administered onto the eye that will dilate the pupil. So that drug in that eye drop can be either an antagonist of the parasympathetic division, an antagonist for muscarinic receptors, or it could be an agonist, mimicking and speeding up the sympathetic division signaling and nerve impulses, so acting on those alpha-1 beta-1 receptors. So the pharmaceutical industry has been very innovative, making artificial molecules like that. What you see listed here is beta blockers that are blocking those beta-1 receptors to slow heart contraction in some heart disorders. Pharmaceutical industry also was very innovative in making artificially some of those neurotransmitters themselves. So using an EpiPen, for example, is nothing else but injecting epinephrine, a cousin of norepinephrine, into the bloodstream. So let's take a look at the last part here. What is the physiological effect? Why do we prize our autonomic nervous system so much? Individual organ systems can be regulated through reflex arcs, whether speeding up or slowing down activity of the digestive system or the heart or respiratory system. On the other hand, there is one area where many organ systems activities are coordinated, independent of individual need, and that is here is the set of reactions that we experience when we are nudged or sometimes shoved out of that rest and digest circumstance. So there are moments in our lives that are stressful, that are causing an alert. So these are emergency situations. You're walking down on the dark street and somebody just scares you. Maybe this is Halloween and it's all for fun, but you're really spooked. Excitement. You are preparing for the comprehensive final, and as you sit down ready to do this exam, the excitement itself takes you out of this rest and digest activity. Embarrassment, especially in cultures where lying is culturally embarrassing and discouraged. This will also trigger the sympathetic division of our nervous system. And this is what all of us experience too, exercise or physical activity. Even if you just do hard manual labor, it may not be fun, or when you go to the gym or go out for that 5-mile run, those are all move us out of this rest and digest state. So what is going to change here in a collaborative, in a coordinated fashion? So in these E situations, emergency, embarrassment, excitement, exercise, we are switched into a fight or flight or fight response. So the first dominating stage was rest and digest. This is the opposite to that, fight or flight. Our hypothalamus, experiencing embarrassment, getting information from the cerebral cortex, identifying a dangerous situation around us or an exciting situation around us. There are many ways our brain informs the hypothalamus that we are exercising. So we create an alarm reaction. The body needs to be ready to either fight, meaning put up resistance, physical force, or run away. Either way, we'll be using skeletal muscle force, which increases oxygen demand, increases glucose demand, energy carrier demand in the body. And so here is what our body, our hypothalamus, directs us to do. Makes perfect sense. Increase heart rate, increase blood pressure is one result. This is in the name of moving more blood to the lungs to carry more oxygen from it, and also to carry more energy carriers to those skeletal muscles and cardiac muscle of the heart. We do have increased blood glucose levels. This is coming from skeletal muscle and also from the liver, that those organs degrade their glycogen store, and glucose is released into the blood, so now we have more energy carrier. We have our airways, our bronchioles dilate, and so now our lungs can process more air. Respiratory rate increases, so more air, more oxygen is moved to the respiratory system, and more oxygen will be getting into the blood. So having more oxygen, more energy carriers, and a faster blood flow because of increased heart rate, all supplying oxygen and glucose to skeletal muscle and cardiac muscle. On top of all that, we have decrease in blood flow to non-essential organs. So those non-essential organs during a fight or flight response are organs of digestive system, urinary system, and so this is why the stomach responds very differently to a sympathetic nerve impulse compared to the heart, because heart activity is expected to increase, stomach activity, and this includes pancreas, small intestine, large intestine, salivary glands are all decrease in activity. The decreased blood flow to those organs just means that the arteries supplying those organs undergo vasoconstriction, so blood vessels constricting, not allowing the regular amount of blood to flow to those organs. The blood is effectively channeled away from these organs towards the cardiac muscle and skeletal muscle. So this is how we achieve increased blood flow to skeletal and cardiac muscles, not only by increasing heart rate, but on top of that, we are channeling blood away from non-essential organs, digestive, urinary, reproductive system. And here's something else. Dilation of pupil occurs. This is maybe the best way to describe this is that When we are fighting an enemy or running away from some kind of danger, we need to see our environment better. And so dilation of the pupils allows more light to enter into our eye, onto our retina, and so we can assess visually the situation better. All this is coming from our nervous system, right? So this can start very, very quickly in a matter of seconds, especially if we are spooked or embarrassed. This can come on out of the blue in a matter of seconds. You would expect that this also goes away in seconds. Okay, the reason for emergency disappears, embarrassment situation goes away, and we should be returning to the rest and digest activity. Except that for some reason our body is programmed to maintain the sympathetic response for at least 15-20 minutes. How can we do that without constant activity of our nervous system? And here comes that ingenious connection to the adrenal gland. If you remember the first part, we saw a wiring diagram where the preganglionic neuron of the sympathetic division ended up in the adrenal gland, and there stimulating release of norepinephrine and epinephrine. So those two molecules, which we call hormones of the adrenal medulla, are released in the blood, and that is the game changer. Once that triggering molecule, norepinephrine and epinephrine, released into the blood from the adrenal gland, all these alarm reaction, fight or flight response reactions maintained until those hormones are taken out from the bloodstream. So one effect of this is that if you are spooked or if you're embarrassed, that feeling stays with you for 15-20 minutes. If you are done with that 5-mile run, at the end of the exercise, your heart rate will slowly return to normal, and it takes 15-20 minutes to get out of that fight or flight response. And for those of you who experienced this with kids, when bedtime comes, it's a very good practice to do some quiet activity before bedtime. Before you turn out the lights, maybe some reading, maybe talking about something. If kids are playing video games all the way till they go into bed, or they run around the house, chase each other, or the parents, or the pets, all that represents fight or flight response. And they will not go to sleep for 15-20 minutes, not because they don't want to, but the epinephrine and norepinephrine in their blood will keep stimulating the sympathetic response, increase heart rate, increase blood pressure, and the increased airway dilation. This all adds up to an excited mental state. And so again, having a little time out before going to bed can make wonders, just because we return them through reading or a long bath into the rest and digest state, where falling asleep is a ton easier. So this is the end of the second part of chapter 15, and I'm going to stop here. Learned quite a bit about the autonomic nervous system here. So most of our life are spent under the domination of the parasympathetic nerve impulses. When we sleep, when we are in a quiet, undisturbed environment, we have in our body rest and digest activities that dominate. This means that there's a conservation of energy and also recharging the body's energy stores. So what creates energy in our body? Activity of the digestive system. So salivation, digestion, and also emptying the digestive system, defecation, is promoted in this state. We also have the instructions for tear production, permission for urination from our autonomic nervous system. So all these organs are carrying out their activity, and along this comes a relatively moderate heart rate, which is roughly 75 beats per minute. The diameter of our airways, bronchioles, are fairly small because in this set of activities we don't need to pump a lot of blood or obtain a lot of oxygen from air. So those organs can take a rest as well. Also, the diameter of the pupil narrows, and all these actions in the body happening during this rest and digest state. Parasympathetic nerve impulses dominate all those dually innervated organs.